So let's have a look then at the Bellman equation in continuous time. So remember, what was the Bellman equation again? In particular, when we have some perpetuity, growing perpetuity, which gives us some profit, some cash flow P each time unit in discrete time, which grows at some constant growth rate. So P at time t plus 1 is depends on P at time t, but it's a little bit bigger. So again, what is the value of an option to buy such or the value basically of this cash flow? You could write it as the expected value of the cash flow that we get tomorrow, discounted. So that's the first part here, plus the continuation value. So continuation value is the value of that stream of cash flows viewed from a point of view tomorrow, which will then depend on the price, the profit level, the P that we've reached tomorrow, t plus 1. Discounted ones, of course, because we're looking at tomorrow. And then the expected value of that stuff. So this we could do in discrete time, so we have to look at the next step. So we take today's value is the expected value of the next step's value, including the cash flow that we get in the next step. Well, this next moment, this next step, does not really exist in continuous time, right? We don't really have this next moment t plus 1 because time is flowing continuously, so there's a continuous flow of time. So the way in which we'll then go about finding what the Bellman equation in continuous time looks like is by taking a limit of this expression in discrete time. And what limit? Well, the limit in which these time steps between different periods become smaller and smaller. So the limit in which these time steps delta t, the difference between time today and time tomorrow, gets to 0. Okay. So let's see what we need to do. We have to see what's going to happen next time. Next time is a time dt from now, where this dt is going to be very small. Well, so what happens? Well, first of all, time itself will move, right? So it will increase from 0 today to dt the next instant, the next second perhaps, or the next millisecond, whatever you wish. During that period of time, we get some cash. How much? Well, depends on how large the cash flow, the flow of cash, the flow rate is, P, times the length of this time interval. So P times dt, that's the total amount of cash that we get in this period of length dt. What will happen as well is that this price in the meantime will fluctuate, right? It's continuously moving, so from price today, P, it will move to P plus dP, where dP is this increment which might be, for instance, described by geometric Brownian motion. And what will also, of course, also move is then what the value tomorrow is. What the value the value of today will go to the value of tomorrow, and the value tomorrow will be the value, but now evaluated at the price or at the profit rate tomorrow. So evaluated at P plus dP. So the questions will be, what in particular, what is this V evaluated not at P itself, but at P plus dP? So ultimately we want to plug this in then in this Bellman equation. So the value today is the expected value of the cash flow that we get, plus the continuation value, which is the value of tomorrow when price has evolved from P to P plus dP, but discounted, and this discount rate, which is, as dt gets very small, gets very close to 1, of course, just slightly smaller than 1. So that's what we need to think about. So what we need to plug in here is, of course, what this V, again, this V evaluated at P plus dP is, and how does it relate to V evaluated at P itself? And how does it depend on this dP that we know, the change in prices that's described by geometric Brownian motion. So now there's some computational steps that go into here. And it will turn out actually that this Bellman equation for this function V as a function of P will satisfy some equation. So this is the equation. You see on the left hand side R times that function will equal on the right hand side this P plus mu times P times the derivative of V plus a half times sigma squared times P squared times the second derivative of V. Well, that's perhaps sometimes a bit unexpected. So indeed, let's take a look at the picture here. I think we should be a little bit more explicit here. So what I have to do now is, what I'm going to do is I'm going to explain to you briefly how we get from here to this equation. And that's not because you need to know this for your exam. So for the exam, you just need to know this particular equation over here. But just to satisfy your curiosity, if you have that about how you get there. But if you don't want to know about this, then it's fine if you just close your eyes for a little bit, and then I'll wake you up when we get at this equation again. So let's go into why, approximately why is this? How do we get from the discrete time Bellman equation to this continuous time differential equation? So what we need to remember here is we first have to figure out what is v, the value function evaluated not at p itself but at p plus dp. And here you have to remember that if you have a regular function, some f of x, then you know that the f of x plus a little bit plus dx is actually related to the height of this function at x itself plus a little bit which will be related to the derivative of this function, because the derivative basically measures how steep this function is. So if you move a little bit to the right, so an amount of dx to the right, how much does your function increase? Well, it depends on the derivative. So that's where the derivative df dx actually comes in. So this is something that you know. It holds actually only completely if you take the limit dx goes to 0. So for very small step size dx, and if you have a larger step size, then you will have corrections to that which will be of order dx squared. The dx squared, if dx is really small, is much smaller actually than dx itself. So that's why this holds in this limit. So this is just the definition essentially of what differentiation is. So if you forget about what differentiation is, this is what it is. This is how it's defined. So can we use that? Yeah, of course we can. What we want to do is we want to say that the value of p not the value of v not evaluated at p itself, but at a very small amount dp moved, say, to the right, if dp is positive, will be the same as the value of p plus the derivative of v times this very small step. And that's again using that using the same rule of differentiation. So we would expect that we could describe this v at p plus dp as vp itself plus this derivative term. As long as this dp is small enough, of course, which will happen if dt gets very small, then dp, change in price, will also get very small, since this is a continuous process. Well, this is almost true, but it's not quite true. And the reason why it's not quite true is because this dp is actually moving not deterministically, but it's moving stochastically. So there's also this dz term, or dz term, this uncertain term, this volatility term in the price movement for dp. So let's have a look at that. What does that have to do with this equation? Well, there's going to be some correction. And the correction is this dz squared. So you remember that dz itself is Gaussian, it's normally distributed, and we know actually that the variance of dz itself is finite. It's sigma squared times dt. So dz squared, a squared term here, actually has an expectation which is also proportional to dt, just like the first order correction. So we cannot argue that as we take this very small time limit, dt 0, that this amount here is going to vanish, because it will have exactly the same size, or the same order of size, also in order of dt, that we will have, that will be present in all these dt terms. So let's see what this amounts to. Well, this is basically what's Ito's lemma. So if you do the derivative scores, or if you want to have a look in the book by Hall, you will see that by Ito's lemma, that's a lemma that holds for derivatives essentially of these functions of stochastic processes. It tells us that the value of a function evaluated at p plus dp is indeed these first bits, so the value at p itself plus this generic steepness term, this derivative term v prime times dp, plus this additional correction where you see indeed that this has a form which depends on the size of the uncertainty term, so the volatility term. You see the sigma squared here, the square of that, times the second derivative of v times dt. So this final term basically results from the squared dz part that we have to also take into account, which has a finite, or an order dt, I should say, expectation. So let's have a look at what that means, or what will happen. Well, what we first do is in this equation over here, in the first line we plug in that we know actually what dp is. So dp is given by geometrical random motion. It's mu times p times dt, so the drift term, plus sigma times p times dz, the volatility term. So let's plug that in. So this term and this term both come from v prime p, so it's multiplied by this v prime p dt and dz. So that's plugging in the value of dp that we have here, plus again this final term that we have here. So now we can get on, because now we can have a look again at this approximation, or this limit that we want to take, which involves not just VP plus DP itself, but the discounted value of that. So we have to multiply this by this discount factor, so e to the power minus r dt, the red stuff here. And also that is, we have to approximate that as well for small dt, and as I mentioned, the dt gets very small, getting very close to 1. So e to the power 0 is actually 1, but there's again a first order correction here, and this first order correction will be proportional to the derivative of this term, which is minus r dt. So this first term here, when you expand that up to level dt, you will get 1 minus r dt. Plus higher order terms, we're going to drop all terms that go to 0 faster than dt. So anything that's proportional to dt squared, which will be correction here, we're going to drop that. And we multiply this by this expression for v evaluated at p plus dp that we just had, which was this thing. And if you add those up, well, we get 1 times v, for instance, which will give us this thing. The minus r dt times v gives us the minus rv times dt over here. The 1 times these other terms over here gives me the the other terms, so mu times p times v prime comes from this one, of course. The sigma p v prime dz times 1 you find over here, and the 1 times half sigma squared p squared v double prime you'll find over here. And all the other terms, so which involve multiplying dt by dt, they will be higher order than dt, so they will be of order dt squared, and those we can rest assured those go to 0 sufficiently fast. So this is what the approximated value to first order dt looks like of this thing that we plug into the Bellman equation. So that's what we just did. So this is what we get. So let's have a look at the Bellman equation and use that. So what was it again? So we wanted to compute the expected value of the cash flows, PDT, plus this discounted value of V evaluated at P plus DP. Well, we're just working on what is this to first order and DT. All the stuff that we have in here except for this P DT term. And now we're almost there, because we're taking the expectation, and well, these are all deterministic things, but this thing actually is a stochastic term, and its expectation is 0. Expectation of dz, it's normally distributed, it's 0. So that drops out upon taking the expectation. So what we're left with is V equals V plus P minus RV plus mu times PV prime plus a half sigma squared P squared V double prime times dt. And this last term drops out. Now you see the V's actually are cancelling on both sides. And if we rearrange by getting the RV term to the left hand side, it boils down to this equation that I started out with. R times V equals P plus mu times P times the derivative of V plus a half sigma squared times P squared times the second derivative of V. And this equation is the Bellman equation. or sometimes often called, actually in this context, the Hamilton-Jacobi-Bellman equation, or HJB equation. Okay, so now it's time actually for all the others to wake up again. So let's go to the important stuff. We have to know now this equation. We have to recognize this equation. Why? Well, in all the papers that we're going to discuss in this course, really literally all the papers, this equation will appear. So we will have to get very used to this equation. So might look a bit awkward right now, but we'll get confronted with it every lecture. So at the end, you will actually dream of this equation. So this R times V equals P, which is the cash flow, plus mu times PV prime, plus a half sigma squared P squared V double prime, or the second derivative of V. So this is an equation that relates the function V, which is a function of this price P, to P itself and to its own derivatives, to V prime and to V double, its first derivative and its second derivative. So you can actually have some intuition for this. What you can, from a finance point of view, relate this to, what we have on the left hand side here is, this is growth in value, right? So this value grows at the growth rate R. What is this growth of this value consist of? What consists of a dividend yield, you might say. There's money coming out of this object, of this instrument, of this asset here, V, which is dividend yield P, that's the money that comes out, plus an increase, because P itself, increase in the value of the asset, so an appreciation of the value, because P itself is increasing, plus some correction for this uncertainty part, which correction turns out to be related to the convexity of V, so to the second derivative of this function V. Just because it's so important, let me also again want to put it here in a frame. So in this frame, again, this Bellman equation. This is the equation that we have to learn by heart, essentially, and we are going to actually also look at it a lot of times, and we're going to solve it a lot of times in the future. So this is it, so this is it for our growing perpetuity, which produces this cash flow P all the time. This P itself might be increasing through geometric Brownian motion. So more generally, what we'll have as this first term here is the actual cash flow, which might be some function of P or something else, actually. It need not be P itself, but these other terms will remain the same always. Okay, as I mentioned, this is called a differential equation. Why? Because it relates a function V to its derivatives, to V prime, the first derivative, and to V double prime, the second derivative, multiplied by its argument P, right? So here we have V, the function V itself, here we have the X, right, the argument of this function, times the derivatives. And what does solving a differential equation mean? Well, it means finding some function V of P that solves this particular equation if you plug it in. So it's this function V of P that we would like to determine. We would like to find a solution to this particular equation. And this Bellman equation basically tells us that there exist these relations between this function and these derivatives. So if you had a little bit of a look at option pricing, then you might recognize that this looks a lot actually like the Black-Scholes equation, and it actually is intimately related to the Black-Scholes equation for option pricing, so for call options and put options, except that well, particularly this Black-Scholes equation also has a time derivative in it, so that's a major part which makes actually Black-Scholes equation a lot more difficult to solve than this Bellman equation. So how do we solve this? Well, let's try to solve this for this particular case in which the cash flows are indeed this price which is moving according to geometric Brownian motion. So this is again the growing perpetuity thing. So how can we solve it? Well, one way of solving equations is by guessing the answer. And here we actually have a good guess because we already essentially know what the price for a growing perpetuity was. We already covered that before. We figured out was P divided by R minus mu. That was the value of a series of cash flows corresponding to a growing perpetuity. So let's indeed check that this expression, this value, indeed solves this particular Bellman equation. So let me do that on paper. So again, we are looking at this growing perpetuity. And we're going to check that the value that we already found before, actually P over R minus mu, since P satisfies this geometric Brownian motion with a drift and a volatility term, that this expression here actually satisfies this Bellman equation. So again, the Bellman equation is R times V equals the cash flow that we get today, plus this drift part times the derivative of V, plus this uncertainty part squared times P squared times the second derivative. So let's check whether actually plugging in V of P, the function V of P that we found, P divided by R minus mu, whether that solves this equation. Well, in order to do that, we need to figure out what is actually V prime P. Well, if V is this, well, the derivative of that will be 1 divided by R minus mu, right? It's a function of P, it's a linear function. R minus mu is just parameters, constants. So taking the derivative of a linear function just gives us this 1 over R minus mu, the factor that multiplies P. And of course the second derivative, well, the first derivative doesn't depend on P anymore. So the second derivative will of course be 0. So the derivative of this thing, but it doesn't depend on P, so it should be 0. So let's figure out whether that actually, if we plug that in, whether it solves this Bellman equation. So let's see, so R times V, well, V is P over R minus mu equals P plus mu times P times the derivative. This was the derivative over here. Let's see if that's true. Well, just let me bring this all under one denominator. So let me write this P as R minus mu times P divided by R minus mu plus mu times P divided by R minus mu. And now we see that minus mu times P plus mu times P, those two cancel. So this one cancels against that one. And what's left here is R times P divided by R minus mu. And indeed, that's the same as this thing, just like we wanted to prove. So indeed, this function V of P, P over R minus mu, it satisfies the Bellman equation that we postulated. Just by, we could just compute that it actually, if you plug it in, it works. So this is sort of a nice confirmation that, you know, this Bellman equation is not complete nonsense. At least things that we know hold actually satisfy that equation. Of course, the great use will be of this Bellman equation will be that we can also compute things that we do not know yet. It's going to be a powerful way to compute those. So let me get back to the slide. So indeed this solves that differential equation. So what we now would like to do is we want to include something. We want to include investment. So we want to have a look at, you know, what happens if today we get nothing, no cash flows, but we might invest some investment cost I in order to get something which depends on some price process P, some profit process P. So that will be the contents of the next video.